Section 9.2, we're going to start studying infinite series. In Calc 1, you studied a little bit about finite series. For example, we had something like the sum from I equals 1 to 100 of I, which was 1 plus 2 plus 3 up to 99 up to 100. And we had some rules for evaluating these sort of things. Anybody remember the rule for how to add 1 plus 2 plus 3 up to some number?
Is it like n plus 1 over n?
Close. Not n plus 1 over n. But it does have an n plus 1 in it. It has an n in it also. All right, so we had a rule. The sum from I equals 1 to n of I, which is 1 plus 2 plus 3 up to n, was n times n plus 1 over 2. So if I want to add 1 plus 2 plus 3 all the way up to 100, that's 100 times 101 divided by 2, which is 5,050. So those are the sort of things we did in Calc 1. Now in Calc 1, what we were doing, if you remember with these sums, we had summations like this that we were using to find areas of integrals, areas under curves, which is how we define definite integrals. And then we were taking the limit as n goes to infinity. So in a sense, we were doing infinite summations, but not exactly. Little brief story here. Last week, we had a division meeting. And in our division meeting, they said that the social welfare committee on campus is trying to raise $5,000. And so the way they're doing it is they're asking one person to donate $1, another person to donate $2, another person to donate $3, all the way up to $100. And they said that adds up to $5,000. And all the math people in the room said that does not add up to $5,000. It's $5,050. So anyway, so they didn't knock out the $50 one. They should have. Then it would have worked. All right, so in this class, in this section, we're going to study infinite series. Also generally just called series. So we're going to have things that look like the sum from I equals 1 to infinity of a sub I. And what I think your book uses n, the sum from n equals 1 to infinity of a sub n. And when we look at infinite series, we're really going to be concerned about two things. Question number 1. Does it converge? What do I mean, does it converge? What's that? When I keep adding more and more numbers, do we get closer and closer to one specific number? That's exactly right. That's what I mean by does it converge. Question number 2, if so, what does it converge to? So those are kind of the two questions we're going to be asking. All right, we're going to have a very formal definition of converge. So for converge, consider the sum from n equals 1 to infinity of a sub n. S sub 1 is just going to be a sub 1. So capital S sub 1 is a sub 1. S sub 2, I'm going to add the first two terms together. I'm going to take a1 plus a2. What do you think S3 is going to be? I add the first three terms, a1 plus a2 plus a3. S sub 4 is a1 plus a2 plus a3 plus a4, so on and so forth, down to S sub n. What's S sub n going to be? A1 plus A2 plus A3, and we stop when we get to A sub n. A1 plus A2 plus, we stop when we get to A sub n. What am I creating here? What's S1, S2, S3, S4, S5, so on and so forth? They are numbers. It's a list of numbers, isn't it? So this will be a number. A1 plus A2, that'll be a number. A1 plus A2 plus A3, that'll be a number. So if I write these this way, S1, S2, S3, up to Sn, and we can keep going beyond that. What have we created? We've created a what? Not a series. This is a sequence. Right? We just have a list of numbers. So, if the limit as n goes to infinity of S sub n converges, then we say the sum from n equals 1 to infinity of A sub n converges also. Converges to the same value. So we start with an infinite series. To tell if an infinite series converges, you create a sequence. And then you test for the convergence of the sequence. Questions on that? All right, so this makes more sense when you have an example. So consider this the series, the sum from n equals 1 to infinity of 1 over 2 to the n. That would be 1/2 plus 1/4 plus 1/8 plus 1/16 plus, we keep going forever and ever and ever. Does that converge? Yeah? What's it converge to? Well, if it goes to infinity, then we don't say it converges, then we would say it diverges. Seems like it should diverge, doesn't it? I mean, if you add an infinite number of numbers together, doesn't it seem like that should keep getting really, really, really big? After a while, these numbers are really small, aren't they? And the numbers that you're adding are so small, they're almost zero. All right, so let's look at our sequence. What's S1? 1/2. What's S2? Not 1/4. 1/2 plus 1/4, which is 3/4. What's S3? 7/8. How'd you get 7/8? It's 1/2 plus 1/4 plus 1/8, which is 3/4 plus 1/8, which is 7/8. Ah, I love fractions. That's great. How about S4? For S4, you would take your previous answer, 7/8, and you would add 1/16. Which happens to be 15/16. So, in general, we're not going to prove this, but looking at the pattern, what would S sub n be?
1.
Not 1.
N over n plus 1.
Not n over n plus 1. What do you have on bottom? You have 2, 4, 8, 16. So S1 had a 2 on bottom, S2 had a 4 on bottom, S3 had an 8 on bottom. So what's S26 going to have on bottom? What's that?
64.
2 to the 26, a lot bigger than 54. So what's S sub n going to have on bottom? 2 to the n. We're going to have a 2 to the n on bottom. What are we going to have on top? 2 to the n minus 1. Right? Because this is 4 minus 1. This is 8 minus 1. This is 16 minus 1. So on and so forth. All right, so what's the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n?
1.
It's 1. Why is it 1?
Because you have the same exponent on top and bottom. Same power.
That rule works when it's n squared on bottom and n squared on top. But in a sense, this really is the same thing. It's in the form infinity over infinity, and your exponents are, in a sense, the same thing. If you don't like that argument, use L'Hopital's rule. What's the derivative of the bottom? Well, I'm not sure what the derivative of the bottom is, although I should know it. Well, what can you tell me about the derivative of the bottom and the derivative of the top? They're going to be exactly the same because the derivative of this 1 is going to be 0. What's the derivative of 2 to the n? There's an ln 2 multiplied by a 2 to the n. It's 2 to the n ln 2. Just like the derivative of e to the n is e to the n. If you have a 2 to the n, you get a 2 to the n, but then you got to fix it with an ln 2. Anyway, so moral of the story is the sum from n equals 1 to infinity of 1 over 2 to the n converges to the number 1. Questions on that? Well, this series that I've written down, this is a special kind of series. Anybody know what it's called when you multiply by the same factor each time? Here we went from a 1/2 to 1/4, so we multiplied by a half. To go from 1/4 to 1/8, you multiply by a half, multiply by a half. Anybody know what that's called? You multiply by the same ratio over and over and over again? No? That's called geometric. Geometric series. Usually geometric series start at 0. For some reason I chose to start that one at 1. That's okay. A geometric series is the sum from n equals 0 to infinity of r to the n, where r is your ratio. Geometric series sometimes converge, and geometric series sometimes diverge. We're going to let S equal the sum from n equals 0 to infinity of r to the n, which is 1 plus r squared plus r cubed plus r to the n, and then it keeps going. And then I'm going to take this series actually, I don't want to go all the way to infinity. I just want the partial sum. I'm going to stop at n. I'm going to multiply that partial sum by r. So when I multiply by r, I'm going to have r plus r squared plus r cubed plus r to the 4th where does it end? R to the, what's the last power? N plus 1. What happens now if I subtract? I'm going to take RS and subtract S. So what happens when I take this thing and subtract that thing?
1 plus Rn plus Rn equals to Rn plus 1.
Close.
Negative 1.
Minus R to the n plus 1.
Well, what's going to happen with this R when I subtract that R? It's gone. How about that R squared with that R squared? R cubes? R to the fourth? What survives?
Those two. Or minus that one.
This one, because right before this one is R to the n, isn't it? So this one survives and the 1.
Close.
That's R to the n plus 1 minus 1. Okay, on the left-hand side now, I'm going to factor out the s. That's s times r minus 1 equals r to the n plus 1 minus 1. So s, my partial sum, is r to the n plus 1 minus 1 over r minus 1.
You always will take those steps.
Well, no, we're going to end up with a formula here, but it seems like one of my signs is backward.
We were subtracting RS from S, right? So it shouldn't be 1 minus R to the n plus 1 instead of R.
No, I'm okay. I'm okay. I took RS minus S, so this one's going to be positive, that one's going to be negative. RS minus S. Now, what's the limit? As n goes to infinity of r to the n plus 1 minus 1 over r minus 1. Sometimes. When is it infinity?
When R is positive.
Close. What if, for example, r is the number 2? If r is the number 2, when n goes to infinity, what happens to r to the n plus 1? You get infinity. On the other hand, what happens if r is a fraction like 1/2? What happens when you take 1/2 to the n plus 1 and you let n go to infinity? You get 0. Right? 1/2 raised to a big power, like 1/2 to the 50th is 1 over 2 to the 50. That's really, really close to 0. So sometimes this converges and sometimes this diverges. When does it converge?
That's a whole number.
Not when r is a whole number. For example, when r was 2, this didn't converge. What kind of fraction? How about if r were 3/2? That's a fraction. If r were 3/2, those 3/2 raised to a really, really big power. A really big number, because when it's less than 1, okay? What if r is -4? What's -4 raised to a really, really big power? Sometimes positive, sometimes negative. So is it converging? No.
So it has to be between 0 and 1.
What if r is -1/2? What's -1/2 to a really, really big number? Sometimes positive, sometimes negative, but ultimately really close to 0, right? Like -1/2 to the 50th is 1 over 2 to the 50, where negative 1/2 to the 51 is negative 1 over 2 to the 51. They're both really, really close to 0, aren't they? So, this equals negative 1 over r minus 1 when r is between negative 1 and positive 1. Otherwise diverges. And this is usually written as, this is why I thought I had my sign backward. Usually we take that and we multiply top and bottom by negative 1, and we write it as 1 over 1 minus r. All right, so for a geometric series, the sum from n equals 0 to infinity of a times r to the n, quite often they have an a in them. A is just some fixed number. That's going to be a over 1 minus r if r is between negative 1 and positive 1. Otherwise, it diverges. All right, so I might ask you, what's the sum from n equals 0 to infinity of 4 times 1/3 to the n? What you would need to do is you would need to look at that and first recognize it as geometric. What tells you that that's geometric? It has something to the n. That's geometric. Does that series converge or does that series diverge? It converges. Why does it converge? Because that r number is between 1 and 1. So your answer would be convergent geometric series. But for a geometric series, you can do even better than that. You can tell me exactly what it converges to. It converges to 4 over 1 minus 1/3. That's 4 divided by 2/3. What's 4 divided by 2/3? 6. So not only does it converge, it converges to the number 6. Questions on that? All right, how about sum from n equals 0 to infinity? I don't know, anybody got a number they like? 13 times 4 to the n. Diverges, how come? Divergent geometric series. R equals 4, which is bigger than 1. Questions on that one?
How does it get hard?
How do these get hard? I don't know. How about .9999 going on forever? How much is that?
Infinitely close to 1.
Infinitely close to 1. Not equal to 1?
So 0.999 going on forever.
Yeah, .999 going on
Are
forever.
they like engineers or mathematicians?
We're mathematicians here. We're in a math class.
Never touches 1.
It's 1?
No.
No?
No. Never touches 1.
Never touches 1? Okay. How about if I were to write it as 9 over 10 plus 9 over 100 plus 9 over 1,000 ... Do you agree with that? What's 9 over 10? 0.9. What's 9 over 100? 0.09. What's 9 over 1,000? And I keep going. I get that pattern, right? Can you write that as a series? Well, what's the A number?
Is it 9 over 10 to the n?
When you say 9 over 10 to the n, is it just the whole fraction to the n?
No, the 10 raised to the n power.
Just the 10 goes to the n power? That's almost right. N
Plus 1.
plus 1. Why n plus 1? Well, if I were to plug 0 in, I would have 9 over 10 to the 0. 10 to the 0 would be 1, so that would just be 9 over 1. That would be 9. Our first one is 9 over 10, so when I plug 0 in, I need a n plus 1. So it's almost geometric, isn't it? What's the problem? How come it's not geometric? What do we have to have for geometric?
R to the n.
R to the n. We have r to the n plus 1. I'm going to fix that. This is the sum. From n equals 0 to infinity of 9/10 times 1 over 10 to the n. Now is it a geometric series? Yes, it has a number times a ratio to the power. Our number is 9/10, and our ratio is 1/10. So does this geometric series converge? Yes, because r is 1/10, which is between -1 and 1. So this converges to 9/10 over 1 minus r. That's 9/10 over 9/10, which is the number 1. 0.999, repeating forever, is just a fancy way of writing the number 1.
So it does equal 1.
So it does equal 1.
So converge means it's getting really, really close to it, but it's not actually there.
Correct. It's our same limit process that we've always done. When I say the limit as x goes to 2 of x squared minus 4 over x minus 2 is 4, it's never really exactly equal to 4, is it? But I can make it get as close to 4 as I want it to be. Yeah, it's the same sort of limiting process. So 0.9999999 can get as absolutely close to 1 as you want it to be, so it really just is the number 1.
It is proved.
Well, let me ask you a question. If this is not the number 1, then is it smaller than 1 or bigger than 1? It would have to be smaller than 1, right? If it's smaller than 1, then shouldn't there be a number between 0.99999 and the number 1?
Yeah.
Okay, so what's that number?
An extra 9.
But these 9s go forever. They go to infinity.
So it is the number.
So it is the number 1. It has to be the number 1. Otherwise, it'd be a number in between. And there isn't one in between. That's the number 1. So it's like a philosophical class today.
Yeah, what? This is math.
0 with an infinite number of zeros and then a 1.
What's that?
I'm going to say 0.0 with an infinite number of zeros and then a 1.
Well, then it's smaller though. 0.0 is less than 0.9.
He's going backwards, like.
I'm saying that's the number that's in between the
Zero.
point zero
You're
zero.
proving it from zero.
Oh, he's saying like point,
One is zero.
yeah, I know.
The number in between that is
I
zero.
don't know how to notate that.
You can prove that the number in between .999 and 1
So what number are you putting there?
is 0.
Point zero with an infinite number of zeros.
But
That's not the.
0.0 with an infinite number of zeros would be over here, wouldn't it?
Oh.
0.0 is less than 0.9.
What he's
He's
doing,
like
we're adding
the
adding
sum,
them
the sum of
together.
them.
He's adding.
He's saying there's.
We're subtracting.
That one's going to be really close to 0.
All right. Well, the moral of the story is you can't do it. All right. Well, you can do that with any repeating decimal.
Oh, please no.
Oh, please. Oh, let's do another one.
Just
Point.
add it.
How about 37, 37, 37, 37, dot, dot, dot. We know it's a rational number. How do we know it's a rational number? It's a decimal that repeats. So if you have a decimal that repeats, it's a rational number, which means you should be able to write it as a fraction. So how are we going to do that? Well, we're going to write it as a geometric series. What do you do? Well, notice this problem we did a minute ago, it only had one number that repeated, just the number 9 repeated over and over again. So we went a 10 and a 100 and a 1000. This new one that I wrote has a block of numbers that repeat. It's got 2 numbers.
So it would be 7 over 10 to the n plus 1.
Yes. So that's going to be, I'm going to write it as 37 over 100. So that takes care of the first block. What do I have to have on bottom to get the next block of 37 into this right spot?
10,000.
10,000, which is 100 squared, right? That's 100 squared. What do I have to have for the next 37 to get it into the right spot? 100 cubed. And we keep going. So this is the sum from n equals 0 to infinity of 37 over 100 times, and then what am I multiplying by each time? 1 over 100 to the n. My first one is 37 over 100, and then each time I have to multiply by a 100. I go 100, 100 squared, 100 cubed, so on and so forth. That's 37 over 100 over 1 minus 1 over 100. That's 37 over 100 divided by 99 over 100. That turns out to be the fraction 37 over 99. Questions on that?
So 37 divided by 99.
He doesn't believe me. He's going to get his calculator out and check me.
That's what the calculator does if you have a decimal and you try to convert it to a fraction.
Like,
I have no idea what algorithm the calculator uses to convert decimals to fractions.
Okay.
Is that right?
Yeah, that's right.
See, of course it's right. All right, so those are geometric series. The other kind of interesting series that we have in this section are called telescoping. The sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1. What's S sub 1?
Just the whole thing over n minus.
1 minus 1/2, isn't it? I just plug 1 in. Put 1 in, I get 1 minus 1/2. What's S sub 2? Well, it's going to be 1 minus 1/2 plus, and then I plug in 2. What happens when I plug in 2? 1/2 minus 1/3. What's S sub 3? Well, it's going to be 1 minus 1/2 plus 1/2 minus 1/3 plus, what do I get when I plug in 3? 1/3 minus 1/4. What's going to happen with S sub n?
Equal 1 minus 1 over n plus 1.
1 minus 1 over n plus 1. Excellent. Why?
Because all of the middle terms are going to cancel out.
Yeah, notice what's happening. Those two cancel each other out, don't they? When you went to S sub 3, the 1/2s cancel out, the 1/3s cancel out. If I were to write down S sub 4, the halves would cancel out, the thirds would cancel out, the quarters would cancel out, and I'd have a 1/5 on the end. So that's why these are called telescoping. Why are they called telescoping? Well, they do go on forever.
Always come back to something.
Not really. Think about a pirate's telescope.
Because you're looking at the farthest point of the end.
Kind of. That's not the way I think of it, though. What can you tell me about a pirate's telescope? They extend. So there's your infinite series. But then what happens when you squeeze them back together? It collapses, and what do you have left?
Same thing. First point.
You have the big ring and the little ring. That's what happens here. This whole series collapses. All you're left with is the first one and the last one. All the other middle ones get hidden and they collapse down on themselves. So, what's the limit as n goes to infinity of S sub n? 1. Which means the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1 equals 1. That's a telescoping series.
What's the details for that?
What's the details for that? The details,
Like, where you can just look at it and know that the...
how can you just look at it and know? All right, if I were to write this down, the sum from n equals 1 to infinity of 2 divided by 4n squared minus 1, I would look at that one and I would right away guess that that one's going to be telescoping. Can anybody tell me why I would guess that that one looks like it's telescoping? The n squared, that's a hint.
Subtraction.
The subtraction, you get closer. Let me ask you a different question. How would you do that? It's a fraction. What can you tell me about the bottom? You have factors. So what do you do when you have fractions in the bottom factors? Partial fractions. Same thing, I'm going to do partial fractions here. That's what tells me this one's probably telescoping. When you have a fraction, the bottom factors, you can do partial fractions, probably going to be telescoping. Well, let's see. 2 over 4n squared minus 1. That's going to be a over 2n plus 1 plus b over 2n minus 1. Clear my fractions. 2 equals a times 2n minus 1 plus b times 2n plus 1. What's one of my favorite numbers in the whole wide world to plug in? 1/2. When I plug in 1/2, I get 2 equals 2b. So b is 1. My other favorite number in the whole wide world? -1/2. I get 2 equals -2a. So a is -1. All right, so I'm going to rewrite this. The positive one we usually put first. So since b turned out to be positive, I'm going to write that one first. 1 over 2n minus 1. Oops, minus 1 over 2n plus 1. Now what you do is you plug in a couple of numbers and make sure it really is telescoping. So I plug in 0. When I plug in 0, I get -1 minus 1 plus. I plug in 1. What do I get when I plug in 1? 1 over 1 minus 1/3 plus. I plug in 2. When I plug in 2, I get 1/3 minus 1/5. And one more just for fun. When I plug in 3, I get 1/5 minus 1/7. Does it look like it's telescoping? Yeah, those reduce, those reduce, those reduce. What's going to happen when n gets bigger and bigger and bigger? That number right there is going to get smaller and smaller and smaller, close to 0. So our answer is, adds up to be the number -1. All right, so that's what tells me telescoping. Telescoping, you're going to recognize things are telescoping when you can do partial fractions. Questions on that?
Will the telescoping ones always have fractions, or could it work without fractions?
I've never seen a telescoping one that didn't have fractions. Because what you're thinking of is something like 1 plus 2 minus 2 plus 3 minus 3 plus 4 minus 4. The problem you're going to have, oops, I should have had one more, right? Plus 5 maybe. The problem you're going to have, these aren't going to get smaller and smaller, they're going to get bigger and bigger. So is the series going to converge? No. So I suppose in a sense that's a telescoping series, but it's not one that converges. That would be a divergent series. Other questions?
So when we use the partial fractions procedure, is that we don't actually integrate?
No, we're not integrating here. But I was just trying to remind you, what would you do with a problem like that? You would do partial fractions to integrate it. To show something is telescoping, always end up doing partial fractions. So when you recognize that you have a series, the a sub n can be factored on bottom and you can do partial fractions, that's your big clue that that one's going to be telescoping. Usually. I won't say it always works, but usually it does. Other questions?